okay, then you put in a CIA element into it. Okay, whenever you want to add to your model, the labor market, people will put the elements of the EMP model. Okay, so it's kind of a very basic tools. Okay, like the Ramsey model, the classical growth, right? So whenever you need this capital accumulation thing and so on, so you want to add this element. So these are the basic building block, kind of a building block in macro research. Okay, now I in my lecture notes, so I have this so the intention is to help you learn the Randy Wright CIA Model 2 notes, and I find that actually this notes is, other than a few typos, it contains a lot of results. Okay, so many results and so many models. Okay, it's really worthwhile to learn it, and then so basically Randy Wright present the material in a very compact and very elegant way. It is a nice lecture notes. Okay, it's a nice lecture. I guess he prepared these results at the University of Pennsylvania. So now Randy Wright is in Wisconsin. Probably waiting for Nobel Prize. Right? So it's Randy Wright. Big contribution to monetary economics, not in CIA, but in search model of money. Okay, everything search. So we don't have time to talk about the search theory of money, but we make a lot of contributions to money, okay, monetary research. Now, this Randy Wright lecture notes, right? So you may want to, if you have the hard copy, you can also open it and make it side by side. But my lecture notes, I try to make it self-contained here as far as possible. Okay, so we start out with the simplest model. Okay, so we start with the simplest model. There's one good infinite horizon, and then representative households, and then the supply side of the model. Okay, so here this is the demand side, and then we try to keep the things as simple as possible. Okay, so the simplest approach is that you keep the supply side, everything exogenously given. Okay, so the supply of goods is something falling from the sky. Okay, so and then this consumer just pick it up every morning. Okay, so this is called a pure endowment model. And then of course you can make the supply side endogenous. Then you will need the labor, right? So later on in this chapter, you want to put leisure into the model, and then the consumer will have a time endowment, and therefore consumer optimally choose the working hours, and therefore the more the consumer work, then it will produce more output. So the supply side will be endogenous, right? Similarly, if you put capital into the model, again, if the consumer save, then you get more capital in the future, therefore you can produce more output, right? So this is endogenous. But here, start out with the simplest approach, okay? And then later on, you add more and more features. So this chapter is very nice, actually. So this ET is something falling from the sky, and then the representative household just wake up every morning, just pick it up from the floor. And then there's you want to put money into the model, okay? Then there's again a demand side and supply side. Now, so here you treat money demand is just like the demand for consumption goods. Okay, so this represent household will choose goods demand, right? Consumption demand or goods demand, and also money demand. Okay, so this is the demand side of the model, and then the supply of money is exogenously given. Okay, so only the government. So government just print whatever amount of money they like. Okay, so in most of the macro model, the supply of money is always exogenous. Okay, so if you want to have an endogenous money, then either you have to make some private money, or you use so in the real world we have government money, right? So unless you want to model the government, then it's better to take this as exogenously given, right? The supply of money is exogenously given. So in this symbol, lowercase letter, this CTMT, the demand, right? So just like you in micro economics, you solve the consumer's problem. Okay, so you get a Marshallian demand curve. This is the solution would be the Marshallian demand curve or demand function for consumption goods, and also the Marshallian demand function for money. Okay. And obviously, demand doesn't mean, if you have the demand function, it doesn't mean realized quantities, right? You need the supply side, the demand and supply, and then together you get the realized amount of goods in the economy, and also the realized amount of money that people will hold. Okay, so that's why you need almost trivially this exogenously given supply, and then you determine the equilibrium. But here, this is the consumer problem. Now in CIA model, if you read all the references, you do see this kind of equation. Now, this one is not hard to understand. You just say, okay, the total amount you want to spend on consumption goods cannot be bigger than the amount of money you have. But this one is harder to understand, actually. Okay. In Williamson, for example, because he tried to put assets into the model, okay, money, bonds, nominal bonds, real bonds, and so on. So it sort of make these things very complicated, and also it is not clear why you need this so-called overall budget constraint. In fact, I found that if you can write this constraint in that way, it's a lot more understandable. Okay. So here, the overall budget constraint, you want to put the total demand. Okay, so the amount of money that you want to spend. Okay, so PDCD is the amount of money that you spend, and then MT plus 1 is the amount of money you want to carry over to the next period. Okay, so this is the total amount of money that you will need today. Okay, and then the right hand side is the total amount of money available. Okay, so you carry over MT that much of money from yesterday, the government give you TT that much of money today, and then the worker of this household sell endowment ET in the market, and then you receive PT ET that much of money. Okay, so the right hand side is the total amount of money available today. Okay, So if there's no CIA constraint, okay, if you work with a non-CIA model, then if all the money arrive at the same time, and then if the shopper can take this total amount of money to shop, right? So this will be the conventional model, okay? But here the key thing is that in the CIA model, the shopper can only take part of the total amount of money, okay? So here it is important to keep in mind the timing, okay? So the CIA model, this is the key things of the CIA model. Okay, so the sequence is critical. Okay, so at the beginning of period T in the morning, the household received money transfer from the government. Okay, this cap PT. Okay, and then also pick up this endowment from the floor. So endowment in real goods. Okay, and then from yesterday, right? So there's that much of money carry over from yesterday. Okay, so then it means that the cash at this moment is MT plus TT. Okay, so that much of money. And then this number 2 is that the household consists of 2 members. So the shopper can only take this available cash, go out to shop. And the endowment actually can be sold for money, but this receipt from the sale of endowment is not available for purchase today. It is available for tomorrow. Okay, so this is how the CIA model works. Okay, put this restriction. So here the worker, okay, another agent of the household, the worker take the endowment, sell this endowment in the market for money, okay? But the shopper cannot take this money, okay? You can imagine they are separated, okay? They go to 2 different places, okay? So the shopper go to one place to shop, the worker go to another place to sell this endowment. And then, so here, even though the shopper knows, okay, understand the worker actually got a lot of money from the sales, but because of the spatial separation, you cannot access this cash. And also, we assume that the goods is a cash good, so that you cannot buy on credit, okay? Now, actually, if you think about what happened in the real world, you will understand what is meant by a cash good and a credit good, okay? Now, in the real world, we have the following scenario, right? So usually, your paycheck, suppose you work, okay? You work for a company, okay? You receive your paycheck by the end of the month, okay? Let's say you receive your salary by the end of the month. Now, during the month, okay, when you want to buy goods, okay, either you have to accumulate cash from last month's salary, or you use your credit card. Now, what's meant by put on credit, right? You see, the idea of using a credit card is that you know your money will come at the end of the month, right? But at the beginning of the month, you don't have money. But then the bank is willing to lend it to you, okay? So basically, you use your credit card. So basically, this is just the same as your endowment, right? Your endowment arrived at the end of the month. You have that much of money, but you can actually buy from credit, just like you can somehow get your endowment earlier, right? Okay, so this is the idea of a credit good. Okay, whereas cash good is that maybe you go to the mall, you want to buy ice cream, and then the seller doesn't want to take your credit card. The seller asks for cash good, right? So this cash good, even though by the end of the month you have $1 million once you receive your paycheck, but still you cannot buy ice cream because you don't have cash, right? Okay, so credit, so this things is so you can compare. Suppose you look at other setup. If you jump to another model, like investment, right? So we can do it like, so for example, you jump a few sections. So you have investment goods and consumption goods. And then let's say you can have a model that you put CIA constraint on consumption goods only. So here, to buy consumption goods, you need cash. However, to buy investment goods, you can put on credit. Okay, so then the constraint would sort of like would be something like that. So this is investment. Okay, this is your total output. Okay, and then this is output minus investment. Okay, so sort of like you can purchase investment good directly from your endowment. It's just like put on credit card, right? Like you have you go to the mall, right? You go to the mall. So by the end of the month, when you receive your paycheck, you have $1,000, and then you put on credit card $500, and then when you receive your paycheck, you just pay it back, right? Okay. So this is just the same thing. So here, this investment good is not subject to CIA constraint. Okay, and of course you can also make the two things subject to CIA constraint. So this is the case, CIA on both goods. Okay, so here you would like something like this, right? So this is investment, and then this is consumption goods, and both of them are subject to CIA cash constraint. Okay, so here, the point I want to emphasize is that different CIA arrangement, right? You can put one good on CIA constraint, the other not on it, but you always end up with the same overall budget constraint. So this is a sort of a common features of all CIA models. So in writing down a CIA model, you can always write down an overall budget constraint. On the right-hand side are all the total money available. Okay, total amount of money available. Even though you cannot get all of them at the same time for shopping, but you can sort of collect together the total amount of money available at time T. And then the left-hand side is the total amount of money you need, okay? Total amount of money you need, including the amount of money that you want to carry over to the next period. Okay. And then different CIA model differs by this constraint, okay? What amount of the goods you need to have cash, and also the availability of cash. So, for example, if you read Williamson or Randy Wright's if you want to introduce asset, then there's a lot of possible arrangement. Okay, so you can do it like, so for example, let's say you have asset trading. You want to introduce asset trading, so the household can put resources on bonds, okay, saving account, okay. So you assume you have these real bonds or nominal bonds, which is saving account, cash saving account. So for example, you can have asset trading first. Okay, so this model one is that asset market opened. So this one is asset market open after the shopper leaves home. Okay, so that the shopper still can only have this kind of cash. But then, even though in the asset market, the household can actually get quite a lot of cash from the dividend or the saving account, but all this cash is available to borrow. Okay. Now you can also have, alternatively, you can make asset market open before the shopper leaves home. But then the shopper will have a lot of cash, right? Including cash carried over from yesterday, new money from the government, and also this net amount of cash that you receive from your dividend and sales of the bonds, right? So you can have CIA model like that, okay? But no matter how you change this CIA, this part is always the same. You see, this overall budget constraint is always take the same form. The right-hand side are the total amount of cash that is available, okay? And then the left-hand side is the total amount of cash that the household will need to spend, including cash to be carried over tomorrow. Okay. So you will see, after we work out a few models, you will see why I want to emphasize this point. Okay. If you read Williamson did not explain why he wanted to do it that way. It's very hard to understand. So I try to explain a little bit better. Okay. Hopefully you will find it more understandable when you read those Williamson and Randy Wright. Okay, but let's go back to our simple model so you understand the timing now. Okay, timing now, and then and the overall budget constraint can be kind of rewrite this way, and this makes it more intelligible actually. Okay, although mathematically they are just the same thing, but if you write it this way, because this so you sort of make it like a identity. Okay, as long as you don't lose any money. Okay, suppose no money will be lost. Then this is just like an accounting identity, right? Okay, during period T, the worker by selling the endowment. So at the end of the day, when the worker come home, the worker will have that much of money, right? The worker. Now the shopper, because the shopper in the morning, the shopper go out with that much of money, and then she buy back, she used up that much, right? So at most, this thing could be zero. So if she use all the money, but might be there's some leftover cash, right? So there's a possibility might be there's some leftover cash. So this thing could be positive, okay? So I make it a parenthesis here, and this thing can never be negative, right? Because of the CIA function, there's no credit, right? So the shopper, because all this cash good, right? So the shopper cannot spend more than the amount of money that the shopper carry out, right? So here, this is the leftover cash, and then this is the amount of cash that the worker receive. And this must become tomorrow's cash balance, right? So it's just like an accounting identity. It's got to be true, right? So this is just nothing but just a rearranging of this overall budget constraint, right? So you just make this negative thing, you move it to the left-hand side, just the same, right? Mathematically the same, but this thing is actually a lot more understandable. So when you write down the model, you often see people just write it that way and then that way. Right? So it's always not a bad idea to kind of rearranging this thing a little bit. So that's why this one, I don't want to write it as a inequality, right? Because I want to treat this overall budget constraint as a accounting identity. However, this CIA could be strict inequality. In that case, there might be some leftover cash from the shopper. So the shopper, when the shopper come home, she still have some cash, right? Didn't spend all of them. And then this leftover cash will be carried over to tomorrow. Right? So if there's leftover cash, then we will say that the CIA constraint is non-binding, right? So CIA constraint binding means spend all, right? Spend all every day, right? A binding CIA constraint, right? So here, and moreover, if you write the overall budget constraint this way, then it's very easy to see why Randy writes that the CIA constraint can also be written into this form. It's pretty obvious because you have, let's say you have these things. Okay, if so this thing is non-negative, right? Bigger or equal to 0. So therefore MT plus 1 minus this PTET should be non-negative. Yeah. So straightforward to see. And then just if you want in real terms, divide by PD on both sides. And as you can see here, so this is force a demand for money, right? Let's say your endowment, right? So this is your paycheck that you will receive at the end of the month. So it is positive. Let's say it is positive, and by this CIA constraint, we put it in this form. The household is forced to carry money overnight. Right? Now, without the CIA constraint, this may not happen. Okay, but with the CIA constraint, then this easy to see. This money demand cannot be 0. Right? Money demand cannot be 0. So just force the house to carry cash overnight. And then this simple example illustrate, right? So let's say the total amount of money available is, in both scenarios, they are both 17, okay? But if you don't have CIA, okay, suppose you don't have CIA constraint, then both scenario 1 and 2 are possible, because you can have, let's say you have, suppose you want to spend $12 on consumptions, okay? But you have everything available at the same time, 17, then this is possible. Or maybe you can have credit, right? Let's say your this month, so you have okay. So let's see here, the shopper. Okay, so the shopper only has $7, but then but then she want to spend 12. Okay, but you actually have the money in total, right? So if you can put on credit card, this is still possible, right? Okay. So there are two ways that make this pattern possible. Either you can put on credit, right? Okay, even though you only have $7 cash, but actually you have this $10 by the end of the month or whatever. If you can put on credit card, you can still spend 12, right? Or maybe all these $17 available at the same time, then certainly this is also possible. But with the CIA, this is no longer possible, right? Because you cannot put on credit and you only have $7 cash, but you want to spend 12, so no way, right? Okay. So you see the difference, right? So the CIA can make it's non-trivial, right? So CIA constraint is non-trivial. And even though you don't solve this problem by dynamic programming, you know it is a restriction, right? CIA is a restriction, right? You will be a lot happier. Just imagine you will be a lot happier if you have all the money available at the same time and then you go out to shop, or you can have credit card, right? Rather than being restricted by this CIA thing. So the welfare cannot be higher than the no CIA, right? So you can, intuitively, you would expect there must be some sort of distortion because of this restriction, right? And this got to be the case, right? Okay. And then because of the distortion, then we can talk about, is there any way you can sort of correct for this distortion, right? So without given CIA is a fact of life, you cannot get rid of CIA, okay? So, but is there some other way that you can somehow correct for the distortion? Okay, so then this is the idea of the Friedman rule. Okay, so the Friedman rule try to make the CIA constraint irrelevant. Okay, in the not in the sense that there's no more CIA constraint, but rather in the sense that you don't care about the CIA constraint anymore. You'll be happy with the CIA constraint. So this is the idea of the Friedman rule. Okay. So basically, the intuitive idea about the Friedman rule is that you want to make holding money very profitable. Okay, make it profitable so that you will be happy to hold money. Okay, you make the consumer will be happy to hold money, because remember that the CIA forced people to hold money, right? Okay, now if it turns out, even though I force you, but actually it is good for you, then this will solve the problem, right? Okay, so basically this is the idea. So when you look at the Friedman rule or the optimal monetary policy, so you keep in mind this kind of things, so this equation. Now, so we follow this Randy Wright handout. So you can write down the Bellman equation this way. So you can use now in the literature. Usually people don't do it that way. So they would just choose the standard control variable. Use CT as the control. Then you will have two constraints, because one constraint would be, so basically you need two Lagrange multipliers if you use this approach. Let's say you use your control variable to be CT, which is of course a natural choice. Okay, state variable, it is still empty. then it is CT here. And then that equation will be a constraint, right? The overall budget constraint, and then this one, CIA constraint. So if you read papers like Lucas and Stokey and other people, they normally do it this way, okay? So you write down a Bellman equation as usual, and then you will have the two Lagrange multiplier. But here, Randy Wright substitute out the C, and then you only have just this in the quality constraint, and then you have just one Lagrange multiplier. Make the algebra simpler, okay? But the final results must be the same, because it's just the same mathematical problem. Okay, so here, just to help you understand Randy Wright a little better, so we use the same approach. So you substitute out the CT, right? Substitute out the CT using the overall budget constraint, and then you have the so use MT plus 1 as the control, and then to take care of this in the quality constraint, you need the Lagrange multiplier here. Okay, and then the simplified notation, right? Because you have all the T plus 1 and so on. So the simplified notation, whenever you see a prime means T plus 1, right? Without anything means time T. Okay. So this is just a matter of notation. And then we do the standard mechanics, right? Standard mechanics. So you need to, I guess we need some exercise to sort of practice on the mechanics. You need this. So for dynamic programming problem, number 1, you write down the Bellman equation. Number 2, FOC. Number 3, envelopes condition. And then here we need something more because we have this in the quality constraint. But this is the mechanics. So you differentiate this thing with respect to M prime, and this is your control variable. So chain rule, right? So this is the C. The whole thing is the C. So U prime C. U dc, and then dc dm prime. So this will give you the minus 1 over p here, right? And then you also have a m prime term here. So just lambda over p, right? So you differentiate this thing with respect to m prime, and then this thing assume differentiable. That will dv dm prime, right? dv dm prime. Okay, let's set it to 0. And then the envelopes theorem, this time you differentiate with respect to the state variable. Left-hand side, dv dm, and then the right-hand side, m appears only in one place here. Okay, there's no more m in the other expressions. And this is the du dc, right? The whole thing is c, du dc, and then dc dm. This will be 1 over p. By chain rule, right? Okay. And then the Kunterka conditions basically says this thing, what you need is this object, okay? And moreover, whenever you want to use the Kunterka condition, make sure that you make this inequality things non-negative, okay? You cannot do it like an ET minus MT plus 1 over PT. Okay. You see, if you don't have inequality constraint, you can do it either way. That would be fine. But with inequality constraint, you need to follow the same convention. Okay. So if you want to make sure part of the necessary condition is the Lagrange multiplier to be non-negative, then you want the inequality. You want to put your inequality constraint this way. Okay, mt plus 1 over pt minus et bigger or equal to 0. Now, if you do it the other way around, everything will be the other way around, right? Then you need to reverse the sign of the Lagrange multiplier. Okay, so the sign matters. Okay, the sign matters. Okay, if you want to treat everything is non-negative, you want to make sure you want to put the inequality constraint as non-negative. It matters. Okay, you cannot mix it. Okay, so make sure everything put in the non-negative form, right? Then the necessary condition, right? So necessary condition is that the inequality will have to be satisfied at the optimal, and then the Lagrange multiplier will be non-negative, and then but the product of them have to be zero. Okay. Now this, so what is meant by this set of equations? So basically, they are necessary condition for the solution, right? In calculus. Okay, so the solution of your maximization problem must satisfy this set of necessary conditions. Okay, the first order conditions. Okay, so now in particular, there's also some confusion. Sometimes if you read papers, people are not particularly careful. Now, it has to do with the under what condition the inequality constraint is binding. Okay, because you have these conditions. Therefore, if lambda happens to be positive, okay, then it must be true that this inequality, this constraint must be binding, right? Because if lambda is positive, you want the product to be zero. The only way is this term has to be zero. Now, however, if lambda is zero, anything can happen here, right? So sometimes people are not particularly careful about this point. They say when lambda is zero, this thing is strictly positive. Not true, right? Okay, so it's not a if and only if kind of condition. Okay, and I can give you concrete examples. So in the lecture notes, we later on I can construct equilibrium that can illustrate this point. Now these things, now in dynamic programming solution, you have this on-forms condition. Now the reason why you need this on-form condition is because you want to substitute out this term, okay? Because when you write down the Bellman equation, when you differentiate this right-hand side, you will end up with dvdm prime, okay? So dvdm prime you want to substitute out, and how do you substitute out? You rely on the on-forms condition. Now, and here, however, is not just strict substitution, because here this is m prime here, this is m here, right? So basically the timing is a little bit different. So here, you see here, you need to realize that this mt, okay, v prime mt, u prime ct over pt for all t, okay, it's not just for one t, okay? Even though it looks like we have three set of equation here, looks like three equation, but in fact it is not, because for each equation is for one time, right? But then we have infinitely many time period, right? So this actually infinitely many equations. You see, because this is a dynamic optimization problem, right? So the solution is a sequence. Okay, C0, C1, C2, and so on. And so you need these infinitely many things. And here, because this thing is meant to be true for all t, therefore, it doesn't really matter whether you write it as t or t plus 1. Because this is meant to be true for t for 0, 1, 2, 3, 4, 5, and up to infinity. See, the point is in infinity. There's no last period. Right? You see, if you have a last period, there's a problem, right? Let's say you have a last period, because you were saying that, okay, this is for C1 for t equals to 0, 1, 2, but then you need 3, then you have a problem. However, remember that this is infinite horizon. So you don't have last period. You will never have this one. You can always, if you set t to be 1,000, t plus 1 is 1,001, but you still have it, right? So you still have it. So that's why you can kind of make these things. You rewrite this thing at t plus 1, right? So m prime, c prime, p prime. Okay. So then you can yeah. So that's just like what I said here. Okay? Kind of like what I said here. Okay. For all t, right? For all t. Okay. So and then you can substitute, right? Substitute and then multiply and so on. So you will end up with, by substitute out this dv dn prime, and you end up with this object. Now, actually, you can see here, you already have quite a bit of kind of a distortion. Okay, so intuitively, you have some sort of distortion here. Because remember that in this economy, every time you have, so every day you have endowment, right? You have endowment. And then there's no savings and so on, right? So if you eat a little bit less today, it won't affect the amount of goods available tomorrow because there's no capital, no savings, nothing. So if you were the social planner, the way you convert a unit of current goods into future goods must be 1 to 1. Okay, so if you give up 1 unit of current goods, tomorrow you have just 1 unit of future goods. There's no consequence, basically. The less you eat today or what has no consequence. Unlike the capital case, right? If you have capital accumulation, this will be different. Right here, so the social planning problem must be the marginal rate of substitution of current goods and future goods must be 1. But here it cannot be 1, right? This ratio cannot be 1 because of this lambda things here. So basically, this CIA constraint put a distortion, right? So destroying the familiar-looking Pareto optimal conditions, right? So your marginal rate of substitution equals to the marginal rate of transformation, and marginal rate of technical transformation in a social planning problem. So there's just notation here. So you see here that there's no prime. Okay, so this pi, Randy Wright defined it that way. So in terms of time subscript, he defined it that way. No, so it's not quite conventional. So usually we want to define it this way. Now, because this is meant to be, now if you, so the meaning of these things, okay, the right hand side, the meaning of this thing, this is the rate of change of the price level from time t to t plus 1, right? So therefore, imagine in a stochastic model without perfect foresight, this object is uncertain as of time t because you don't know pt plus 1. You have to forecast. Okay, so in a stochastic model, if you define it this way, then pi t is actually unknown at time t. Okay, it will realize at time t plus 1. Okay, so this can actually, because of this notation, if you define it this way, if you're not careful enough, this can cause quite a lot of confusion. Okay, in a model in which you don't have perfect foresight, unlike the setup here, because here you know everything. Okay, you know everything. You have no random shocks and so on. Okay, however, if you define it this way, as this is the most popular one, this will kind of suggest that this pi t is known at time t, which is true because pt is known, pt plus pt minus 1 is known, right? So that's why this is a more popular notation. Okay, less confusing, maybe put it this way. Now, if you use the more conventional notation, your Euler's equation sort of looks like this. Then and then in the other hand now, I have already explained why 1 over the gross inflation rate